The observable universe pertains to the segment of the universe that we can witness and examine using telescopes and various scientific instruments. However, our capacity to observe is constrained by the characteristics of light, which acts as the primary source of data about the cosmos. Light travels at a limited speed, implying it takes time to arrive from distant entities. This establishes a boundary on what we can see, as we can only view objects and events within a specific range. This limit is frequently referred to as the observable universe, which does not imply it encompasses the entire extent of the universe, but merely the portion we can presently detect with our technology. Furthermore, this boundary is dictated by the duration that light has taken to traverse since the universe's inception. Since we are perceiving light that has journeyed from extremely distant entities, we are effectively viewing those entities as they existed in the past, not as they are now. The diameter of the observable universe is approximated to be about 93 billion light-years, significantly larger than the estimated age of the universe, 13.8 billion years. This inconsistency arises due to the universe's expansion, causing objects to drift away from one another. Consequently, light from certain objects requires a longer time to reach us. The universe is an immense and mysterious expanse, and although we have amassed considerable knowledge, much remains to be uncovered. The James Webb Telescope, alongside other sophisticated instruments, provides new opportunities to enhance our comprehension of the universe's structure, composition, and history. These devices enable us to investigate cosmic phenomena that have remained enigmatic for centuries, revealing new layers of intricacy in the cosmos. What exists beyond the observable universe is one of the most profound inquiries in cosmology. To explore the furthest reaches of the observable universe, we would need transportation methods that exceed current human technology. Concepts such as wormholes or distortion engines, which could theoretically permit us to manipulate space and time, have been suggested as potential solutions for such a task. However, these notions are still vigorously debated among scientists, many of whom contend that faster-than-light travel is unfeasible, as it contradicts the laws of physics as we presently comprehend them. Despite these hurdles, the notion of surpassing the light speed limit continues to be a topic of fascination. Even if such technologies could eventually materialize, they would require advancements in machinery and a profound understanding of the universe's fabric, both of which are currently beyond human reach. The theory of cosmic inflation, which proposes that the universe expanded exponentially just after the Big Bang, suggests that the actual extent of the universe is immensely greater than the observable segment. Indeed, it may be at least 1, 0, 23, 10, 23 times larger than the area we can perceive. This figure is so vast that it is nearly inconceivable for the human mind to grasp. While we can only observe a small portion of the universe, scientists persist in speculating about what may exist beyond the observable boundaries. Theories regarding unobservable regions are constructed upon the data we have accumulated from studying distant galaxies, and NASA plays a crucial role in this endeavor. NASA, in conjunction with other space agencies and research organizations around the globe, has made numerous significant contributions to our understanding of the universe. Even before the James Webb Telescope became operational, NASA had already released images of the ultra-deep field captured with the Hubble telescope. When the James Webb Telescope debuted, it was employed to observe the most distant galaxies ever documented. These images unveiled the presence of countless galaxies illuminating the distant cosmos, seemingly as they appeared millions of years after the Big Bang, which transpired approximately 13.8 billion years ago. The universe's expansion causes the stretching of light to longer wavelengths, enabling the James Webb Telescope to detect infrared light. This has allowed us to observe galaxies forming in the early phases of the universe's history. The James Webb Telescope has recorded observations of several regions of distant galaxies, permitting scientists to study the rate at which stars formed in the nascent universe. These data indicated the presence of a substantial population of galaxies that were generating stars during those initial stages. The findings are truly captivating and thought-provoking. For a considerable time, humans have pondered the possibility that we are solitary in this vast universe. However, these new insights within the observable universe lead us to believe there must be millions of galaxies in the unobservable region of the universe. This notion is genuinely astonishing and evokes a sense of awe and wonder about the cosmos's vastness. Are there extraterrestrial beings somewhere in the universe? The probability of life beyond Earth has never been more compelling, prompting us to consider the potential existence of extraterrestrial entities. There are countless planets outside our solar system, termed exoplanets, which have been identified using methods such as the transit technique and the radial velocity method. Some of these exoplanets may possess Earth-like features and support life. This hypothesis has been bolstered by another discovery facilitated by the James Webb Telescope concerning the exoplanet WASP-96b. This planet is located outside our solar system, and its light spectrum reveals something unexpected: the presence of water molecules. Furthermore, the spectrum indicates signs of haze and clouds, which were not previously thought to exist on a potentially habitable planet. Considering habitable environments discovered elsewhere in the universe and advances in the search for exoplanets, it is challenging to dismiss the possibility that alien life exists beyond our planet. Although we do not yet have definitive proof, discoveries and evidence suggest that the existence of extraterrestrial life is a captivating possibility. What about the multiverse? In connection with the vastness of the observable universe, the possibilities are limitless. The notion of the multiverse, also referred to as the many-worlds interpretation, is a theoretical concept in physics and philosophy that implies the existence of multiple parallel universes or dimensions beyond our own. The multiverse is primarily discussed within the realm of quantum physics, which examines the behavior of minuscule particles like atoms and subatomic particles. According to some interpretations of quantum physics, the act of observation can cause a quantum system to collapse into a singular state. However, in the many-worlds interpretation, the act of observation merely leads the system to split into numerous states, each representing a different outcome. It is crucial to recognize that the idea of the multiverse remains highly speculative and is not yet backed by definitive evidence. Consequently, it is difficult to assert with certainty whether it is a valid concept or not. Some scientists and philosophers find the notion of the multiverse intriguing and potentially useful in elucidating certain phenomena, while others are doubtful about its validity. Given our lack of knowledge regarding what exists beyond our universe, the possibility of a multiverse remains as plausible as the famous Schrödinger's cat thought experiment or the nature of dark flow. It is a concept that evokes fascination and contemplation but necessitates further research and evidence for confirmation. Consequently, the phenomenon referred to as dark flow is indeed present. The investigation is complex and presents a fascinating challenge. Dark flow appeared in 2008 as a possible explanation for the observation that certain galaxy clusters seem to move more rapidly than expected based on the matter distribution in the universe. The concept of dark flow suggests that these galaxy clusters may be influenced by some type of dark matter or dark energy that pulls them in a particular direction. Nevertheless, the existence of dark flow remains disputed and has not been widely accepted by the scientific community. Some research has indicated that dark flow could be real, potentially linked to a massive structure in the universe exerting a gravitational pull on galaxy clusters. However, other studies have not verified dark flow's existence and propose that the observed motion of galaxy clusters might stem from alternative factors, such as systematic errors in galaxy measurements. While some investigations hint at its possible reality, we cannot conclusively affirm its presence beyond the observable universe. Further research and evidence are required to enhance our understanding of this captivating phenomenon. As we delve deeper into the mysteries of the universe, we encounter the idea of dark matter, which comprises approximately 27% of the universe's total mass-energy content. Although it cannot be detected through conventional means, its presence is inferred from gravitational influences on visible matter, such as galaxies and galaxy clusters. This elusive substance is crucial for the formation and structure of the universe. The behavior of galaxies indicates that they are surrounded by extensive halos of dark matter that hold them together, even though the visible matter is insufficient to explain their gravitational binding. One of the most compelling pieces of evidence for dark matter arises from observations of galaxy rotation curves. When astronomers measure the rotational velocities of galaxies, they find that stars on the outer edges rotate at speeds that do not decrease as expected based on the visible mass. Instead, they maintain higher velocities, suggesting the presence of unseen mass. This has led to the development of various dark matter theories, including weakly interacting massive particles, WIMPs, and axions, which are hypothetical particles that could make up dark matter. Moreover, the idea of dark energy has emerged as a significant force driving the expansion of the universe, accounting for about 68% of it. Dark energy is thought to be responsible for the observed acceleration in the rate of the universe's expansion. This groundbreaking discovery was made in the late 1990s through observations of distant supernovae. As galaxies drift apart, dark energy acts like a form of anti-gravity, counteracting the attractive force of gravity on cosmological scales. Researchers are continually investigating the nature of dark energy, and several theories have been proposed. One prominent hypothesis is the cosmological constant, introduced by Albert Einstein in his general relativity equation. Another possibility is quintessence, a dynamic form of dark energy that changes over time. Understanding dark energy is crucial for comprehending the ultimate fate of the universe, whether it will continue to expand indefinitely, come to a halt, or ultimately reverse into a big crunch. In addition to these enigmas, the study of cosmic background radiation provides valuable insights into the early universe. The cosmic microwave background, CMB, is a faint glow leftover from the Big Bang, permeating the cosmos. Detailed measurements of the CMB have revealed critical information about the universe's age, composition, and curvature. Analyzing fluctuations in the CMB helps cosmologists understand the distribution of matter and energy in the early universe, allowing us to reconstruct the evolution of cosmic structures over billions of years. Furthermore, the exploration of gravitational waves, first detected in 2015 by the LIGO Observatory, has opened a new pathway into the universe. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects like merging black holes or neutron stars. Their detection provides a novel approach to observing cosmic events that cannot be accessed through traditional electromagnetic radiation, such as light. This new observational technique is transforming our understanding of astrophysical processes and the nature of gravity itself. The relationship between black holes and galaxies also draws considerable attention in contemporary astrophysical research. Supermassive black holes, located at the centers of most large galaxies, are believed to exert a significant influence on the formation and evolution of their host galaxies. The link between black hole growth and galaxy evolution remains an active field of study, with many inquiries focused on how these massive entities impact star formation rates and the distribution of galactic matter. In recent years, the discovery of exoplanets has surged, with thousands of planets identified outside our solar system. These revelations, particularly through missions like Kepler and TESS, Transiting Exoplanet Survey Satellite, have sparked intense interest in understanding planetary systems and the conditions necessary for life. Scientists examine the atmospheres of exoplanets using transit spectroscopy, searching for signs of habitability such as water vapor, methane, and other biosignatures. The pursuit of extraterrestrial life extends beyond simply identifying potentially habitable exoplanets. Missions like the Mars rovers have been pivotal in investigating the geology and climate of our neighboring planet. Evidence of ancient riverbeds and minerals formed in the presence of water suggests that Mars once had conditions favorable for life. Similarly, moons like Europa and Enceladus, with their subsurface oceans, are prime targets in the quest for microbial extraterrestrial life. As we explore these celestial bodies, the field of astrobiology emerges as a multidisciplinary effort that combines aspects of biology, chemistry, and planetary science to comprehend the potential for life beyond Earth. This research aims not only to discover life but to understand how life might arise and evolve in diverse environments. Ultimately, the philosophy of cosmology invites us to ponder the implications of our findings. Questions concerning the nature of reality, the significance of existence, and humanity's place in the cosmos are profound and far-reaching. As we gather more data and develop new technologies, we must also reflect on the ethical dimensions of our explorations, including the potential consequences of contacting extraterrestrial life and our stewardship of Earth within the context of a vast interconnected universe. In summary, the journey through the cosmos is filled with complexity and wonder. from the search for dark matter and dark energy to the discovery of exoplanets and the study of gravitational waves. Each revelation brings us closer to understanding the universe and our role within it.